We're going to find this volume of a solid, and I'm going to make it as easy as possible for you. We've got this base, which is the region bounded by y equals x squared, and y equals the square root of x. And then if we take cross sections going into the coordinate system, those cross sections are squares. If you take a look at this applet, kudos to the creator down in my description, you can get a better idea of what this looks like. We are looking right now down at the coordinate system, but if I change my view here, I can actually get a better view, and I can see that my base now is that kind of curved diamond shape, and I've got just one square as a cross section. Let me go ahead and add several more squares so you can get a better idea of what our shape actually looks like. Okay, so I've got like 30 squares in there. Let's go ahead and just rotate this around a little bit so you can see what it looks like. So you can see that kind of a fish shape there on the bottom as my base. And as I turn this around, those squares actually create kind of a rounded shape. Now, the really cool thing about the calculus is I can take just a single cross section here. Let me go back to a single cross section, and I can stack infinitely many of these up using my integral. Let me go ahead and create what we're going to look at in terms of the integral. So the integral that creates this volume is going to stack up all of those squares, and each of those squares has some thickness. So we're going to take the area of my cross section times my thickness. And if I take a look at that square that I've got bounded in that region, my square's thickness is in the x direction. So the square's thickness is a dx. So that gives me my thickness. And I know that the area is going to be the area of a square, which is side squared. So I'm starting to piece this thing together so that I can do the computation. I also now that I know that my thickness is in the x direction, I also know that my variable of integration is going to be x. So I need my limits of integration to also be those x's. If you take a look at the graph, you can see that this volume, or if you're just looking at the base, the volume starts at an x value of 0 and it stops at an x value of 1. Now I need to deal with this side. So I can see from my graph that the side is bound in between my upper curve, or the square root curve, and the lower curve. So the side is the distance between those two curves. So my side is going to be the upper curve, which is the square root of x, minus the lower curve, which is x squared. And that's going to be true for any of our squares along our interval. Let's go ahead and put that volume together now. Our volume is equal to the integral. I'm going to span from 0 to 1 along the x-axis. And I'm going to take a side squared. My side is represented by the square root of x minus an x squared squared. So there's my side squared times my thickness. Let me go ahead and move this up so we've got a little more room. I'm going to go ahead and square that quantity inside of my integral. So radical x minus x squared, radical x minus x squared. As I square that, I've got the integral from 0 to 1. Radical x times radical x is equal to x, and then I get an x squared radical x times another x squared radical x. That's going to be two of them, so minus 2x squared radical x. And then on the end, I've got an x squared times itself. That's going to be plus x to the fourth, and this is all dx. Now I'm going to be able to use a power rule. The only one that I've got to change in terms of working on a power rule is my x squared radical x. This is actually an x squared. The square root of x can be rewritten as an x to the 1/2 power. As I add those together, I get x to the 2.5 power, or x to the 5/2. I'm going to use that form so it's easy to apply my power rule to. So my integral is the integral from 0 to 1, x minus 2x to the 5/2 power, plus x to the 4th power dx. This is the easy part, right? Now I can go ahead and apply my power rules. I integrate, I get x squared divided by 2 minus 2. I'm going to go ahead and add a 1, which is actually adding a 2 over 2 to this middle term. And that's going to give me minus 2 times x to the 7 halves divided by 7 halves plus x to the 4th goes to x to the 5th divided by 5, and I'm going to evaluate that from 0 to 1. Let's go ahead and simplify this a little bit further, just continuing to work the math through. I'm dividing by a 7 halves. Well, that's the same as multiplying by a 2 sevenths. So as I simplify this antiderivative, I get x squared divided by 2 minus 2 times, and I'm going to write that as 2 sevenths, x to the 7 halves plus x to the 5th divided by 5, and I'm evaluating this from 0 to 1. I want to apply my fundamental theorem of calculus part 2, so that's going to be the antiderivative evaluated at 1 minus the antiderivative evaluated at that lower limit of 0. But take a look, every single term up in my antiderivative has a 0 in it. So when I evaluate it there, it's just going to be 0 minus 0 plus 0. So I don't need to worry about this. Let's go ahead and evaluate our antiderivative at 1. That's going to give me 1 squared over 2, which is just 1. Minus 2 times 2 is 4 sevenths. 1 to the 7 halves is also 1, plus x to the 5th, so that's going to be a 1 divided by 5. I could find a common denominator and add all of this up by hand, but why bother when I can do this with my graphing calculator? I'm just going to type this into my TI-84, and then I'm going to convert to fractions. So I'm going to go 1/2 minus 4 sevenths plus 1/5. You can hit enter, but I'm going to convert this to a fraction. So I'm going to hit my math key and then choose convert to fraction by hitting enter and then enter again. And we get our answer of 9/70ths. You are doing so great with these. Take a look at my next video. It is also on volumes with integrals. Thanks so much for watching.